Okay, so it's time to look at static equilibrium and torque. We talked a little bit about it in class today, but let's get a little clearer grasp. Okay, so up until now, when we've been putting forces on objects, we've always considered the objects what we would call point objects, meaning that they didn't really have any dimensions, so all the forces that were acting on them would be acting through the same point, okay? But in real life, objects have dimensions. And so lots of times when there's a force, more than one force acting on an object, they're not acting through the same point. And if they're not acting through the same point, they can make that object, so not necessarily translate, not necessarily move back and forth, but they could make it rotate around a point, okay? So it might be the person's belt loop hooked to the wall, but it could be any point, okay? So if this object is hooked, this will rotate. It means we need to go back and look at motion again and realize there's actually two different types of motion, okay? Because even though the sum of the forces might be 0 here, right? This might be 100 newtons going this way. This might be 100 newtons going this way. There's still going to be some motion, even though the sum of the forces is 0. There's not going to be what's called translational motion, which up until now is actually the type of motion we've been looking at. And you know translational motion from math, right? When you translate a function, you pick it up and you move it from one spot to the other. So the whole object is moving, okay? So if there's no translational motion, it means the object is staying in the same spot. But if there's translational motion, we're picking it up and we're moving it over. In order for there to be translational motion, the sum of the forces then, or when there's no translational motion, the sum of the forces must be 0. Okay? The other type of motion, though, that we're now going to begin to look at is called rotational motion. And rotational motion happens even if the sum of the forces is 0, right? The object doesn't move, the body doesn't pick up and move from spot to spot, but it rotates around the spot that it's on. Okay, and again, you would have done this in math with functions where you would have left the function in one spot but rotated it 90 degrees or 180 degrees. Okay, so translational motion, it might have a horizontal or a vertical shift. Or translation, rotational motion is when you're spinning it about a point. Okay, when the sum of the forces is 0, it would mean there is no translational motion. When the sum of the torques is 0, and the symbol for torque is a Greek T, because we've already used up all the T's, then it means no rotational motion. Actually, when the sum of the forces is 0, we say the object is in translational equilibrium, because technically it could be moving at constant speed. Translational equilibrium. And when the sum of the torques is 0, it's in rotational equilibrium. In real life, one can be true and not the other, or they can both be true. Think about the wheels on a car. Right? They are both, on a good day, they are both rotating and translating. Right? They are rotating around their center, and they are also moving down the road. If you spin, there's no translational motion, just rotational motion. If you slide, there's no rotational motion, just translational motion. So it is possible to have, on an object, to have an object doing both of them, and that could be a good thing, and doing either one or the other could be a bad thing for the example of the car. Okay, so if the sum of the forces are 0 and the sum of the torques are 0, if the object is in both translational equilibrium and rotational equilibrium, then we say it is in static equilibrium. Okay, so static equilibrium is when they are both true. but they both do not have to be true. Okay, so for static equilibrium, has to be both the sum of the forces and the sum of the torques must equal 0. Must be both in translational equilibrium and rotational equilibrium. All right, so now I've thrown around that word torque several times, but we haven't really talked about what is torque. Okay, so, well, I already said that torque, its symbol is the Greek letter T, called tau, T-A-U. And what is it? Well, it's not a force, but we could say that it's an influence which causes an object to tend to change its rotational motion. So again, if we think of a meter stick being held in one spot, someone hooked by their belt loop, I apply a force. This force is going to want to make the object rotate. Agreed? Now, how big of a force I apply is going to determine how quickly it rotates. How big of a force I apply is going to determine the amount of torque. But torque isn't just dependent on force. What else would determine how easily or how difficult it would be to make this object rotate? You could even think of, if we were in my classroom, well, one of us is, and it's not you. In class, I would be at the back cupboard, standing at the back cupboards, and I would open a cupboard door. And I would pull it back here, and then I would push from the handle, and because the cupboard door rotates, right? It swings in. That means I'm applying a torque. But what happens if, instead of pushing out here where the handle is to close it, that I push right next to the hinge? If I push right next to the hinge, those easy peasy cupboards that I can just swing in easily if I push out at the edge, it's almost impossible to close them. Okay, the other thing that torque is dependent upon is how far away from the pivot point is the force being applied. And this how far away from the pivot point is this force being applied is often referred to as the lever arm. And those of you who have ever tried to get a bolt or a screw out that's really, really tight and you're using this minuscule screwdriver or wrench, you probably know to go and get a longer handled one. Because getting a longer handled one means you're applying the force a further distance from the pivot point, and it's going to give you more torque even though your force is limited. Okay, so torque is dependent on both on how big the force is and how big the lever arm is. Some of us are limited by how big of a force we can put on. We're limited by those bulging muscles in our arms. And so when that happens, we need to use our physics brain and say, I need a longer R. If you're a Big Bang Theory fan, there was an episode where they were Sheldon and gang were in a van, and the van had a flat tire, and none of them could get the lug nuts off the tire. They had that, that torque wrench. It's the wrench that's like 4-pronged. Okay, so they had this wrench, but none of them were strong enough to get it off. So they took a branch of some kind and they stuck it in one of the prongs. And then like in the next screen, Howard is out here jumping up and down on the branch, trying to get the lug nut off because here's the tire that it's attached to, right? So they extended their R because they were limited by their F. Okay, it didn't work, and they did all kinds of other things that I might find the video for you. But okay, so torque is dependent not only by the force that you apply, but also the distance from the pivot point that force is applied. There's another thing it's dependent on too. Torque is a vector. And torque is equal to R cross F. And everybody who's in Science 12.2 just went, because when you cross multiply two vectors, and if you remember from grade 11 physics, we dot multiplied F and delta D for work, and we got W is equal to F delta D cos theta. It's one way of multiplying vectors, and what you get out is a scalar. But when you cross multiply vectors, it's the same as multiplying the magnitudes of the vectors together by the sine of the angle between them. So our equation for torque is actually are